Hey everyone, my name is Efim Boieru, and I'm representing Encode, an identity verification company. And I'm leading a face liveness team at Encode, so we basically check in front of the camera we have a real person. So what exactly is face liveness? So we all went, after the COVID, we all went through this process of creating a digital identity when we need to present our face and also our documents, and then we create a new account. So we want this process to be as simple as possible, quick, easy, and like fast, yeah, right? But on the other hand, another thing that we want is that this is a very secure process. We don't want somebody to use our identity, our face, and create a fake account and, I don't know, take a loan or something, or do some other illegal activities. So security is another criteria that we want to have. And basically, face liveness or face anti-spoofing is about answering the question, is there a real person in front of the camera or a fraudster, a spoof attack? And fraudsters know a lot of ways to attack. This is just one example. This person is using a printed photo of Mike Tyson, and we call it a 2D mask because it has the shape of a face. And let's see the result. So he managed to bypass the liveness check at some software company, and this is of course not the expected behavior. We obviously want to be able to detect this kind of attacks. And you all know about deepfakes, right? So now they became really, really popular, and like this video is actually a deepfake driven by a fraudster on the left-hand side. And yeah, you see that it is quite realistic. And that's also a vector of attacks that we want to be able to tackle. So there is a huge landscape of presentation attacks, as we call them. So there, first of all, like a big group is impersonation attack, when a fraudster uses somebody else's identity. So that can be, as we saw, like it can be a 2D mask, or it can be a printed photo, or it can be a photo shown on a display, like a small display or large display, or it can be a 3D mask, like in all those movies, like when you wear a 3D mask, very realistic one. So, and also, of course, deepfakes, like face swaps, synthetic faces, and all kinds of deepfakes. There is also another group which is called evasion attack, and that's when fraudster tries to change their appearance so that they look like not like themselves. So they want to basically avoid recognition by the system. So effectively, probably they want to create a new identity. Let's say to get one more loan. So they can have different motivation. So you see, that's a very big landscape of attacks, and our goal, like as a company, is to detect all of them on a very high level. Let's look at these three examples. Do you think that any of them are a spoof attack? Who thinks it's the first image on the left? Raise your hands. Okay, no one thinks. Who thinks it's in the middle? Okay, and on the right side? Okay, all right. So most of the people think that the spoof attack is the third one. Let's see. Let's remember these faces and see later we will go back to them. Okay, so in our industry we have a huge debate between passive versus active liveness. So what is that? Basically, you can see on the video on the left, this is a passive experience. For the user, it's just like making a selfie. And that's, of course, very fast, very convenient. You want to go through a simple process as possible. You get real-time performance. But on the other hand, because of limited data, limited input data, it is harder to achieve high security. And also, because of that, usually simpler algorithms are used. Let's look at the active liveness approach. So this guy rotating head, so we all went through this probably during the last couple of years when we need to rotate our head, or we need to rotate the camera, or we are subject to lights of different colors shining at maximum brightness. So this kind of experience, which is not really convenient, and we don't want to do it every day. We don't want to have it like in public places or stuff like that. Another problem, actually quite important about active liveness, is that it's really hard to statistically benchmark this performance, because like usually to benchmark you have like a predefined data set, let's say 100,000 videos, half of them are real selfies, half of them are spoof attacks, and you run different algorithms, different approaches, you compare their performances. And here it's impossible, because by design it requires each user to run through the process like at this exact moment. So you cannot create some data set in advance, and you cannot compare basically the performance. But on the pros side, you get more input data from the user, and that's why probably it's easier to achieve high security. But let's talk about, like, so we are all here because of AI, so let's talk about a little how it was progressing in the last couple of years. So, like, let's start with vision transformers, which appeared like 4 years ago and revolutionized how we look at generalizability of algorithms. So we are not anymore like specialized. We can have very broad domains where we can reach high results. Then we got vision language models that my colleague Renat was talking about yesterday, and these are basically merging language embeddings and image embeddings into one space, and that way you get richer data representation that you can utilize for better performance of the model. And after that you have multimodal models that are using, in addition to that, even like depth, infrared input, and other modalities that, of course, the more modalities you have, the more performance you can get if you have this data, of course. And as one example is foundational depth models. That's when, like, it's basically zero-shot depth map prediction based on a single RGB selfie. So, given all these advancements in AI, is this dilemma still valid between passive and active experience? So my hypothesis is that if we utilize the most advanced AI, really good data, and by that I mean multiple inputs, video, having good training and test datasets with high variety, diversity, plus keeping passive experience, we can achieve ultimate spoof detection while keeping easy and real-time user experience. That's the hypothesis, and I'm going to test it with 2 experiments that we will be discussing right now. To put it simple, so the current problem statement that is being used mostly by passive liveness approaches is that you have just a single input, an RGB selfie in one moment of time, just a photo, right? One data point. And what is our vision is that if you should add on top of RGB multiple other modalities like depth, motion, and any available modality that you can measure on your device or you can estimate, plus go from a single moment of time to multiple time points, like basically going from a photo to video. That way you get from one data point, you get O of ND data points, basically geometrically more data. And effectively you get the effect of presence right near the person who is going through the face authentication. So basically you are right there, and you can check if it's a real person or not. So let's talk about the first experiment. It's depth enhanced face liveness. I already mentioned a multimodal model, so that one of the examples which is really successful is language bind. So what it takes is that there is a language encoder that maps into language space embeddings, and then you have many other input types, and for each of them you have a specific encoder that maps this particular input to the same embedding space of the language. So effectively you have all these inputs mapped in the same space. That means that they can complement each other, and that's why you get like richer information about what's happening on the scene. And what's the experiment setup? Let's imagine that apart from an RGB selfie, we also have a depth map. Let's assume that we have that. Then we pass the RGB selfie through the image encoder, we get image embeddings. And the same with depth map, pass it through depth encoder, we get depth embeddings. And then we process them, for example, we concatenate them. And so that's, we don't change anything, we just use the existing layers and everything, weights, we don't retrain anything. And we just train a classifier that takes this input embeddings and answers the question, is it a spoof attack or a real person? And for this task, we collected 10,000 spoof attacks of 2D nature, which means that they are flat. So it's like either a photo shown on a screen, or a printed photo, or like a 2D mask, stuff like that. Obviously, divided into train, validation, and test. And important note that for the depth source, we used the true depth camera from iPhone. So let's have a look at the data. That's the visualization of embeddings that are obtained from our training data with the language bind. And when we saw that, we were amazed how well we can distinguish between like normal selfies and all the other spoofs. So you see blue dots are actually normal selfies, and there's a great separation between them. And also another interesting thing that you can even separate different spoof attacks between each other, like the red ones are masks and the orange ones are replay attacks, which means that they are shown on the screen. So let's get back to this selfie. I mean, probably you already guessed that it's not a real selfie. So it looks very realistic. It's like completely normal. But that's the depth map corresponding to it. So you see that it is completely flat. And like a normal face is not flat. So this is actually a photo shown on a large display, so we cannot see the borders. But obviously, if we train a model on embeddings from RGB and depth, then we expect to have great performance. And that's what we have here. So on this plot, we see a comparison between the red curve, which is depth-enhanced model, and the green curve, which is the baseline model that we've been developing, like we had developed before for a long time. And you see huge, like dramatic improvement, 10 to 30 times better spoof detection rate, which is just basically out of the box. You just use another modality, basically. Okay, you might say, yeah, great result, cool, but how do we get depth? Like, not all devices, like iPhones, have depth prediction. So how do we do that? And again, we go back to AI. So as I mentioned, there are foundational depth models that are becoming better and better recently. And one of the examples is depth anything v2. And on the left-hand side, we can see a normal selfie. And for that selfie, we have very accurate and detailed depth map. And on the right-hand side, there is a photo of like a printed photo, right? And it is flat as expected. So of course, it's not like a silver bullet. You still need to configure it, you need to fine-tune it because it might not be well enough on specific domains, but the initial results are really great. So that's definitely, this kind of models have huge potential. All right, so we talked about using one more modality, but what if we use just RGB modality, but go from a single frame to a video? So going back to the image that we already saw, we are fixed on this single modality RGB, and we go, we are analyzing all the frames at all timestamps. So basically, we take multiple frames. For them, we compute embeddings using some backbone that we have been developing before, and based on that, we develop a classifier, as in the previous experiment that we discussed. And optionally, we can take maximum of single frame and video models so that we have ultimate security. So let's have a look at the results. On the left-hand side, we have results on physical test dataset, which means physical attacks from the physical world. We see that errors became 0 on detecting spoof. So we basically detect all the spoof attacks, while false negative rate, which is basically false rejection rate, became also less. That means that we reject less normal users. So two things improved at the same time. And then the question is, like, how is that possible? Why there is no trade-off? And the thing is that we got more understanding of the scene. We got more knowledge about the scene. And when you get more knowledge, there is not necessarily a trade-off. So you can improve in both orthogonal directions. And the same result with deepfakes test data, we see a huge improvement. There is one famous dataset in the world of face anti-spoofing, MSU MFSD. It's basically videos of normal selfies and of 2D attacks. So these are videos shown on a screen or like printed photos, but the borders are not visible. So we call it borderless attacks. So they are kind of realistic. So again, this video liveness model was able to get zero performance. So it's like 100% accuracy, which is, of course, the ideal performance that you expect from any classifier. And like, obviously, the model didn't see that before, so that's a great result. And again, it almost worked out of the box. It's like almost no fine-tuning or whatever. So going back to the example. So this guy, again, like most of you thought that this is normal selfie. Let's have a look at the video. So yeah, you can see that this photo is shown on some display, and obviously you can find frames where borders are not visible, but also you can find frames where these are visible, and that means the video-based model is able to catch that spoof attack. And this one, okay, you understood that this is not a normal selfie, and that's the video. Yeah, you see that this behavior is not really human-like, it's kind of unnatural, and there is a lot of abrupt changes, and basically video model is able to catch that. And the single frame model that uses just a photo was not capable of doing that. So we just discussed two approaches, two experiments. One is combining RGB plus depth, and another one just taking a video instead of single frame. And we showed that actually there is no trade-off. So you can keep the same experience for the user, passive experience, quick experience, without asking them to do anything. But inside, like on the backend side, you can run a lot of different approaches, different ideas, most advanced AI with proper data, and you can get a completely new level of performance. And that's what we believe in, and that's the direction that we think the whole industry should go in. So thank you very much for your attention, for coming to this talk, and If you're interested in solving this kind of tasks, we are hiring, so feel free to reach out to me. Thank you very much.
Thank you. Now it's time for your questions. I hope we have some questions in the audience, and we have plenty of time for them. So maybe you can use the time to ask Efim any questions you would like, and of course wait for the microphone to reach you so we can hear you loud and clear.
Oh, and thank you for your talk. I didn't quite understand about the depth data. Is it gathered from a sensor on a cell phone, or is it estimated using a model?
So, okay, so in the experiment that I described, the depth data is collected from a true depth sensor, true depth camera from iPhone. So it's like measured.
Any other questions from the audience? Yes, here in the fourth row, I guess. Yeah, over there.
Hi, I wanted to ask about the computational cost of using videos instead of images. Also, since we're introducing the new model in your approach, when you use the def anything, I think the model is called, how does that affect the process? Does it add a lot more compute to it, or is it more optimized?
Okay, great question. Thanks for that. So regarding the video model, like in this particular experiment that I described, it's a very simple idea when you just run like the single frame backbone multiple times. So basically you multiply the inference time by the number of frames that you use. So it scales up. But you can do it obviously much more optimally if you work on that. And regarding depth, so again, it's like the idea that we use is to take this language bind model. And I mean, of course, it's not the most lightweight model out there, but comparing to other models that we are using, it's basically more or less on the same range. So it works fine.
Yeah. Thank you.
Thank you.
Well, it seems that's about it for now. Thank you very much for joining us, and please have a little sign of appreciation from the organizers. Thank you very much. Please, a warm welcome. Yeah.